Welcome to the continuation of dimensional analysis, bringing in word problems and what we call double-decker problems. It's going to build off of what you practiced, so hopefully the video will be quicker and you're going to be able to use dimensional analysis to do some slightly more complex problems. So everything that we used in last night's video are base units, right? Instead, now we're going to bring in something we call derived units. We create derived units by multiplying and dividing base units together. So, for example, we could work with density in Unit 2. You're going to do a lot of that. Those units are grams over milliliters. Volume can have the units of centimeters cubed, which is really centimeters times centimeters times centimeters. Even though you can kind of play around with it as a conversion on its own. When you go to physics, you're going to learn about force. The units of force are the Newton, but in reality, when you're doing the math, it's really kilograms times meters over seconds. And if you were to see that in dimensional analysis, you would end with all of those units, as opposed to just one or two. So that's what we're going to be looking at in this video is multiple units at the end of your problem. So here's the nice thing. Double-decker problems are exactly like normal problems. It's just instead of starting with one unit, you're going to have two units, and you're going to have one unit on top, and you're going to have one unit on bottom. Otherwise, you're going to follow all of the exact same steps. So let's look at example number 1. I want to take 55 miles per hour, and I want to know what that is in kilometers per minute. So I'm going to start with what I know. I know miles over hours, miles per hour. So I'm going to have 55.0 miles over hours, right? You see that slash right there? That's the line, the middle line of our train tracks. So I have miles over hours, and I know what some of y'all are thinking, like, what number should go down there with hours? You don't have to put a number down there. It's implied that it's a 1. So if you really are freaking out, you want to put a number, put a 1. If you don't want to put the 1, you don't have to. What's important here is the units. Step 2 of our process, right? Figure out my ending point. I want to end with kilometers over minutes. So I'm going to have to turn miles into kilometers, and I'm going to have to turn hours into minutes. So multiple things are going to be changing. All you have to do is pick one at a time to work with. So it doesn't matter which one you do first. Let's just change hours into minutes first. And hopefully you know that conversion off the top of your head. 1 hour is equal to 60 minutes. But if you forgot or if you didn't know, it wasn't one of the ones we had to make you memorize. So you could ask us and we would tell you. But I want to write it, right? I want to write it and get rid of hours. I start with hours. I don't want to end my problem with hours. So if hours is on the bottom right now, I want to put hours on the top and minutes on bottom. That way when I go in and start plugging in and doing all my math, a lot of my units cancel, my hours on the bottom are going to cancel out the hours on the top, and I'm going to be left with just the unit of minutes on the bottom of my problem, which conveniently is what I want, right? I want minutes on the bottom. I still have to change miles to kilometers. If you don't know that conversion off the top of your head, again, it's okay. It's an English to a metric, so we would give it to you. If I have miles on top, when I get rid of miles, I need to put it on the bottom so that the miles on top at my starting point will cancel out the miles on bottom later in my problem. So I do know a conversion directly between miles and kilometers. I know that for every 1 kilometer, that is 0.621 miles. My miles cancel out my miles. And if I look at my units, I have kilometers on top, I have minutes on bottom, and conveniently, that's what I wanted to end my problem with, kilometers over minutes. I multiply everything on top together, I multiply everything on bottom together, then do top divided by bottom. So I get 55, if I start parentheses, 55 times 1, close parentheses, divided by 1 times 60 times 0.621, close parentheses. Everything on top divided by everything on bottom, and that tells me that 55 miles an hour is actually equal to 1.48 kilometers per minute. Right? Kilometers over minute, kilometers over minute. Last thing I always have to think about is significant figures. I start with 3, so I should be ending with 3. Your calculator is obviously going to have a really long string of numbers. I think it's 1.4761133795 or something like that. So you want to round that so your final answer has 3 sig figs. Let's do the next one. Example number 2. $2 per pound, but I want to know what that is in cents per ounce. So step 1, think about what I have. I have money, I have dollars and pounds. So $2.50 in or over pounds. And again, you don't have to put a number down there, but if you really want to, it's just 1. That's divided sign there is my middle line of my railroad tracks. And I want to convert that to cents per ounce. Both of these are not ones you have to memorize, but maybe you already know them, which would be fantastic. But for every $1, you have 100 cents. Right? My dollar is going to cancel out my dollars. I'm going to be left with cents. And every 1 pound is equal to 16 ounces. Again, and you don't have to memorize that. I just happen to know that one. Pounds cancel out pounds, and I'm left with cents over ounces. Conveniently, that's what my problem wants, cents per ounce. So I would take everything on top multiplied together, divide by everything on bottom multiplied together. So on your calculator, in parentheses, 2.50 times 100 times 1, close parentheses, divided by 1 times 1 times 16, close parentheses, and you should get something in the neighborhood of 15.625 cents per ounce. Last thing you got to worry about is sig figs. If I look back at the start of my problem, 2.50 has 3 sig figs, so I'm going to round my final answer to 15.6 cents per ounce. So not only can we use dimensional analysis to work with double-decker problems, we can also use dimensional analysis to solve the dreaded thing that you always panic about in math class, that guess what, now it's in science class, word problems. Don't freak out when we give you a word problem to solve. You're going to be able to handle it. The way you need to approach it is you just need to start pulling out all of the important and relevant information first. So here we have example number 3. An electric car gets 2.5 miles per watt of charge. The average cost to charge the electric car is 11 cents per kilowatt. How much does it cost the driver to travel 18.5 miles to work? Well, I'm going to go through this again, and I'm going to pull out all of the important looking information. 2.5 miles per watt, 11 cents per kilowatt, and lastly, 18.5 miles. So I got 3 important pieces of information. Conveniently, the 3 important pieces of information are the numbers and the units that go with those numbers. And the way you need to approach these problems is you need to look through what you have and start with your simplest value. When I say simplest here, I don't necessarily mean smallest number. What I mean is the one with the least number of units attached to it. So if we look through our information, these two, the 2.5 miles per watt and 11 cents per kilowatt, have 2 units each, whereas 18.5 miles only has 1 unit. So simplest in this case means we're going to start our dimensional analysis with 18.5 miles. And then we're going to do the dimensional analysis problem exactly like we normally do. Step 1, know where you start. I start with miles. Step 2, know where I want to end. I want to know costs, all right? I want to end in cents, okay? Well, if I'm going to try to get to cents, I have to get to kilowatts first, right? That's how these 2-unit systems work. I can convert from one thing into the other. So if I want to end with cents, I have to get to kilowatts first. If I'm going to get to kilowatts from miles, well, I can't get to kilowatts, but I can get to watts. So I'm going to next put my 2.5 into my dimensional analysis, 2.5 miles. Notice I put miles on the bottom because I started with miles on the top, and that's going to be per 1 watt. So I've used this one. I've used my 18.5. The only thing I have left is this 11 cents per kilowatt. I have to be able to match either cents or kilowatts. I currently have watts in my problem. I need to get to kilowatts, which means we got to bring in one of our prefixes. We know that for every 1,000 watts, we have 1 kilowatt. Now we can bring in our final conversion factor and say that for every 11 cents, we have 1 kilowatt. Typing all this into your calculator, right? Everything on top multiplied together divided by everything on bottom multiplied together, we get 18.5 times 1 times 1 times 11, clothes parentheses, divided by, sorry, I had to retype something in my calculator real quick. There we go. 18.5 times 1 times 1 times 11, close parentheses, divided by 2.5 miles times 1,000 times 1, close parentheses there. So again, everything on top in a set of parentheses divided by everything on bottom in a set of parentheses. And you should end up with, I'm going to kind of fill it in over here because I'm out of space, 0.0814 cents. Last thing I had to think about is Sig Figs. So if I look at what I started with 3 Sig Figs, 18.5, and I'm going to end with 3 Sig Figs, 0.0814. I know some of y'all want to look over here and say, oh, but Mr. Flato, the 2.5 had 2 Sig Figs, the 11 had 2 Sig Figs. Right, but we're going to treat those as exact numbers, aka they have an infinite number of significant figures. When it comes to dimensional analysis, just use the simple kind of rule of thumb. Whatever number of sig figs you start your problem with is the number of sig figs you should end your problem with. All right, last example, example number 4. In the lab, you measure out a sample of hydrochloric acid that weighs 15 grams. Being the brilliant chemist that you are and will be, you know that hydrochloric acid has a molar mass of 36.46 grams per mole. And you obviously have memorized that for every 1 mole, you have 6.02 times 10 to the 23rd molecules. How many molecules of hydrochloric acid have you measured? Most of you have no clue what most of these units are. Maybe the only one you've heard of is grams. Or maybe you know what molecules are, at least an idea of molecules. The beauty of dimensional analysis is it doesn't matter whether or not you know all of these what all these things are. You just have to know how they relate. So going back through the problem, pulling out important stuff, 15 grams, we see 36.46 grams per mole, and that we know for every 1 mole, we have 6.02 times 10 to the 23rd molecules. Again, looking at my information, 15 grams has 1 unit, 36.46 grams per mole has 2 units, and we have an actually written conversion factor here that's going to let me convert between moles and molecules. So I got 2 units kind of involved there, which means when I start my dimensional analysis, I'm going to start with my simplest piece of information, 15 grams. I can use this thing right here because I have grams to match up. So 36.46 grams in 1 mole. Then I'm going to be able to use this last conversion factor. 1 mole is equal to 6.02 times 10 to the 23rd molecules. 15 grams, grams cancel grams, moles cancel moles. You're left with molecules, which if I look back at my problem, is exactly what I wanted to end with. So I knew what I started with, grams. I knew what I ended with, molecules. I've now plugged everything in. My units have all canceled. I'm going to pull out my calculator. 15 times 1 times 6.02 E23. Hopefully you're still using that E function. All of that in its own set of parentheses, divided by 36.46 times 1, which leaves us at a very long string of numbers, 2.47668, some more after that, times 10 to the 23rd. The last thing we always have to worry about is Sig Figs. If I look at my dimensional analysis problem, I start with 2. I'm going to round my final answer to 2. 2.5 times 10 to the 23. Hopefully this gives you a good understanding of more applications of dimensional analysis. Come to class tomorrow with questions so that we can go over it. You will need dimensional analysis. You will have to be able to do double-decker and word problems as we go through the year.